Karnaugh maps are a tool for optimizing Boolean networks. More specifically, they can take a Boolean network arbitrarily defined by a truth table and then condense it to the smallest form of a two-level network, where the network consists of a series of AND gates on the first level to a series of OR gates on the second level. So here we're going to learn how to use the Karnaugh maps by example. So as I said previously, a Karnaugh map is basically a way to convert a truth table into an optimized digital logic circuit. So let's start with the truth table. Here we have a sample truth table with three input variables, I, j, and k, like so, and we have 8 input combinations. So to define our table, we can first put this in the Karnaugh map form. So we're going to say I is on this side, and then j and k are over here. So we will first format our table as a set of 2 rows and 4 columns. And what this will do is it will give us 8 entries, similar to the 8 entries we have in our truth table here. Now, how many possible values are there for variable I? There are 2. We have value 0 and value 1 binary variables. For j and k, we have 4 possible values. We have 0, 0, 0, 1, 1, 0, and 1, 1. So we can list them here as 0, 0, 0, 1, 1, 0, and 1, 1. Now we are using this funny order here called gray code counting. Now the reason we are interested in gray code counting is we want to change only 1 bit between counts. So, for instance, we can say 0, 0, 0, 1, 1, 1, and 1, 0. So if we go from 0, 0 to 0, 1, the LSB changes. From 0, 1 to 1, 1, MSB changes. From 1, 1 to 1, 0, LSB changes. And when we wrap around, the MSB changes. Only 1 bit is changing at each possible step. And this is why we use the gray code counting. Now this property, where only 1 bit changes from one count to the next, is very useful for grouping and finding a minimal number of logic gates, as we will see in a moment. So let's take our truth table over here, and we will then move the entries over. So I, j, and k are all equal to 0, f is equal to 1. I is equal to 0, j is 0, k is 1. F is equal to 1 again. Now we have I 0, j 1, and k 0. The f value is equal to 0. Oops, I'm sorry. That's 0, 1, 1. We're looking at 0, 1, 0. Output is 0, so it goes in this box. Very important gray code counting format. Then we have I equal to 0, j equal to 1, and k equal to 1. F is equal to 1. Now we look at I equal to 1. We are going to the second row. J and k are equal to 0 and 0 respectively. So we enter a 1. And now for the remaining 3 values, it's going to be 0, but let's go through these in detail. 1 for I, 0 for j, 1 for k. So this will be 0. And then here, gray code counting format, I is 1, j is 1, k is 0, f is equal to 0 again. Finally, I, j, and k are all equal to 1, f is equal to 0. Now that we have converted our truth table to the Karnaugh map format, we now need to group ones by powers of 2. So we can use 1, 1, 2 1s, 4 1s, etc. So we can look here and we see a group of 4 1s that are adjacent to each other. But this is not what we're getting at. This is incorrect. What we need to do is group powers of 2 that are in line with each other. So we can do this pair and this pair. So no bending, first of all. We can also group square values. So if we had a 1 value here and a 1 value here, we would be able to group this, but this is not the case, so we will not do that. We have now come to a point where we cover all ones with groups. So we know that all the groups are covered. So f, what is f equal to? Some function of I and j. Well, this is our first group. Notice that j is equal to 0 and k is equal to 0 for this group, but I, we don't care what the value is. So j is equal to 0 and k is equal to 0. We say j prime, because 0 inverted is 1, so that gives us a 1 value, and k prime, because k is 0, k inverted is 1, and so anding together, we know that it has to be equal to 1. Now we come to the second group. Notice here, for these two columns, k is equal to 1. J, we don't care. Notice that I is equal to 0 for this row. So for this group, we say or. So either this group is covered or this new group is covered. We can say I prime anded with k, because I is equal to 0 and k is equal to 1. And now that we have covered all groups, we have our final Boolean expression. F equals j prime k prime or I prime k. Let's draw the digital logic circuit now. So we will say we have I, j, and k. And now we will draw I prime, j prime, and k prime. We need all three of these inverted variables, right? So let's draw these. And we need our inverters to develop these. Inverter 2. And inverter number 3. Now, we can just convert our Boolean expression to a digital logic circuit directly. J prime anded with k prime, I prime anded with k, and then we can OR these together. And this gives us our final value f. So one nice thing about this is, on an aside, we can convert these 3 gates here all to NAND gates by just bubbling the center, because this is called sum of products. So we use and product, so it's like multiplication. Or is like addition. It uses an addition symbol, so we use the word sum. Sum of products. We can convert this all to AND gates if we have a sum of products format by just placing a inversion at the output, an inversion at the output of each of these AND gates, and an inversion at the input of each of these each of the inputs of this OR gate. So an inversion to an inversion and an inversion to an inversion. If you invert twice, it is a null operation. And we now have 3 NAND gates and 3 inverters. Pretty useful. Okay, so now let's try another example. In our second example, we're going to use A, B, and C to an output function h. So now in the previous example we had we didn't have A, B, and C. We had I, J, and K. We had I, J, K in this format like so. One interesting thing to note is that the K-map can be drawn differently. We could say I, J, K with 2 columns and 4 rows instead, and we would get the same result. We could also reorder the variables, and we could say J, I, K like so, and this would still give us the same result. So keeping with this theme in mind, where we can use multiple formats for the Karnaugh map, let's try to use 2 columns instead of 2 rows this time. So we'll have A, A, B, and C, like so. And let's draw this out. So 2 columns, 4 rows. 0 and 1 for 2 possible values of C. And then we need to label A and B values in gray code format. 0, 0, 0, 1, 1, 1, 1, 0, like so. Now let's go down the list and move the values from the table over. H equals 1 for 0, 0, 0. 0, 0, 1, H is equal to 1. 0, 1, 0, H is equal to 0. 0, 1, 1, H is equal to 1. Okay. 1, 0, 0, H is equal to 0. 1, 0, 1, H is equal to 1. 1, 1, 0, H is equal to 0. 1, 1, 1, H is equal to 1. Now, looking for powers of 2, I see this large group of 4 in line. I'm just going to take that right now, and I'm going to say here H equals. C is equal to 1 here, so we can say our first term is C. Our next term, we need to cover this 1 here. Now there are 2 possible ways to do it. We could cover it like so, very easily, and we could say A prime, B prime, C prime. And this would give us an optimized digital circuit. But it is not the most optimal, it is still suboptimal. So instead, we can find another group of 2, and we can cover it like so. H is equal to C or A prime and B prime. So we're covering 2 possible values, or 2 ones instead of just a single one, a singleton. Notice that for A equals 0, B equals 0, C equal 1, if we plug in, we can say H equals 1 or 0 prime ANDed with 0 prime, right? This equals 1 or 1 ANDed with 1, which equals 1 or 1, and that equals 1. So by using the larger group, we eliminate this extra input. So we don't need to use a 3-input AND gate. We can use a 2-input AND gate instead. Let's draw the circuit. A, B, and C. And what do we need? We need 2 inversions for A prime and B prime. Draw 2 inverters. And now we need 1 AND gate for A prime and B prime. And then we need an OR gate. Because C is not ANDed with anything, we can take the C value and wire it directly to the OR gate, like so. And we have now our output H. So, just to make sure that you believe me, we can now try doing this table in a different format. A, B, C. Let's do the previous case where we had 2 rows and 2 columns and verify that we'll get the same result. So A can be possible values 0 or, 1. And then we count in gray code format 0, 0, 0, 1, 1, 1, 1, 0. So 1, 1, 0, 1, right? 0, 1, 0, 1. I just went right down the list from here, and as you become more proficient, you'll be able to just copy directly by going down the line. I recommend that you take the time to think about this step by step if I went a little bit fast for you. But this is the correct format. So here we need to get a group of 4. Take a look. 1, 2, 3, 4. We've got a group. So that's 4 together as a group. It's not bending any corners, so we're doing well. And then we have this group of 2. So we need to say, well, these 2 columns represent C equal to 1, and we don't care about what the value of A is, so H is equal to C, ORed with this group right here, A prime, and then these 2 columns, B is equal to 0, so B prime. Notice that this result for the Boolean expression for H is exactly the same as this result here. So the table format that you use should not matter. You should get the same result. A more complicated example using 4 variables. 4 variables. So let's try thinking about this here. We need to use gray code format again. Let's put 2 variables on one side going down and 2 variables going across. So we need 16 entries for 4 variables. And let's count by gray code counts. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. A, B, C, D, 0, 0, 0, 0. G is 0. 0, 0, 0, 1. G is 0 again. 0, 0, 1, 0. G is 0 again. 0, 0, 1, 1. And G is, or D, yeah, G is 1. 0, 1, 0, 0. G is 1. 0, 1, 0, 1. 1 again. 0, 1, 1, 0. We get a value of 1. 0, 1, 1, 1, and we get a value of 1. You may already be seeing some interesting groups that we can choose. 1, 0, 0, 0 is 0. 1, 0, 0, 1 is 0. 1, 0, 1, 0, 0. 1, 0, 1, 1, we get a value of 1. 1, 1, 0, 0, output is 1. 1, 1, 0, 1, right here, output is 1. 1, 1, 1, 0, output is 0. 1, 1, 1, 1, and we have an output of 1 again. So we're looking for groups of powers of 2, groups of 1s that are powers of 2. And we want the largest powers of 2 we've seen. Largest powers of 2. Optimize circuit. So I see this group of 4 right here, where C equals 1 and D equals 1 right off the bat. That's pretty nice. I also see this group here. And now I've covered a lot of 1s except for these last 2. Which group is good? I could cover this group and get one of them, but then I still have 1 left over, so this is not helping us. I could get these 2 by covering like so, and it's the largest group that's a power of 2 that covers those 2. So let's run with that. So G equals CD for this first group on this column, or A prime B for that row, and then we have this cluster here where B equals 1 and C is equal to 0, or B C prime, like so. Notice that we don't care for this set of rows and this set of columns. For this term, BC prime, we don't care what the values of A and D are. So now we have an optimized Boolean expression. We can now draw our digital circuit. Like so. A, B, C, D. We need A prime and C prime, so only 2 inverters. And we develop our inverted variables here, A prime, C prime. And now we need 3 AND gates. C and D. A prime and B. B and C prime. And now these all go to an OR gate, like so. And we have our output G. We have a total of 6 logic gates. So while starting from truth tables is fairly straightforward for the Karnaugh map, generally we start with a Boolean expression or maybe already start with a digital logic circuit. So let's try a more indirect problem with Karnaugh maps. F equals A prime C or A prime B or A B prime C or BC. How many variables do we have? We have A, C, B, so 3 variables. So we'll need 8 entries in our truth table when we construct it. But let's go directly to the Karnaugh map instead. So A, B, C. Like so. 0, 0, 0, 1, 1, 1, 1, 0. Remember, gray code format. So A prime C. When A is 0 and C is 1. Notice that A is 0, so we need this row here. And C is 1 here and here on this row. Now, let's look at A prime B. So A is 0 again on this row for these 2 columns. We have B equal to 1 here, and for the first column, right here, it's already labeled as a 1, so we don't need to fill it in again. That is covered by the A prime C term. Next we have A B prime C. So A, so we don't need this row, but we need this row. A B prime C, let's mark here. Right? So A B prime C, we've covered that third term now. And then BC. So BC, we need this column only. So this is covered, so we don't need to enter it again. And so we enter this here. Okay? And that covers all our possible values of 1s. So the rest of our entries are defaulting to 0. We now have a Karnaugh map that we can use to find an optimal Boolean expression. Well, here is a group of 4, very clean. And here's a group of 2. So, let's do it this way. F is equal to C, because for these 2 columns, C is equal to 1. And then for this group of 2 1s, A is inverted, A prime, and we have B equal to 1. So A prime B. F equals C or A prime B. Very clean. So we can draw the digital circuit. A, B, C. And then we need only one inverter for A. and we get A prime. And now we need one AND gate for A prime B. One OR gate to OR A prime B with C. And we get an output F again. So here's a rather complicated looking Boolean expression that we can try to optimize with a K-map. How many variables do we have? We have 4, A, B, C, and D. Let's try laying out the K-map now. A, B, C, D. 16 possible values. So we'll have 4 rows and 4 columns. Like so. Remember gray code counting: 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And now we can start filling in the details. This complicated looking Boolean expression is actually a whole lot simpler than it seems. We can see that for any variable that is primed, we get a 0, and for any variable that is not primed, we get a 1. Each of these terms has 4 variables ANDed together, so it represents a single 1 on this K-map. So our first term, let's look at A prime, B prime, C prime, D prime. A prime, B prime, C prime, D. A prime, B prime, C, D. A prime, B prime, C, D prime. A prime, B, C prime, D prime. A prime, B, C, D prime. A prime, B, C, D prime. Then we have A, B, C prime, D prime, like so. A, B, C, D prime. Then we have A, B prime, C prime, D prime. A, B prime, C prime, D. A, B prime, C, D. And A, B prime, C, D prime, like so. All of the remaining entries are zeros. So now we need to cover all the powers of 2, all groups of 1s that are of size powers of 2. So one thing we can see immediately is that we're looking at 2 columns and 2 rows. So we have 4 1s in each group. So notice here that we have several groups that fit nicely into sets of powers of 2. But if we look closely, it is possible to improve the optimization from 4 groups to 2. The key to understand is that Karnaugh maps are like donuts. They're toroid in properties. So we can take this group here and then wrap it around the edge to combine it with this group over here. Notice that for these 2 columns, C is equal to, not C, D is equal to 0. A, B, and C are don't cares. right? So our optimization of wrapping a group around will give us our best result here. In this case, can you see another group that can wrap around the edge? If you said that you could wrap this group of 4 and combine it with this group of 4, you would be correct. Notice here that for these two rows, B is equal to 0, and A, C, and D are don't care again. B equals 0, A, C, D are don't cares. Very nicely. This gives us our most optimal Boolean expression. F is equal to B prime or D prime, because we have two groups that wrap around the edge. Very, very clean. So what is our optimal circuit here? Well, we can use sum of products form, but there are no product expressions. It's just two inverters and an OR gate. So we can say B or A, B, C, D. Well, we have 4 input variables. 2 of them we don't care about, so we can actually drop them. So this gives us B prime and D prime. Like so. And we get F. Now, it's important to realize that while we have this developed from the K-map and sum of products form, we do not always get the most optimal circuit. The Karnaugh map gives us the most optimal sum of products circuit. But we can optimize this circuit further by saying, well, we have an OR gate with 2 inversions, like so, B and D. This gives us F. But this is the same as a NAND gate using De Morgan logic gates. So B, D, and F. So this complicated Boolean expression up here is simply F equals B ANDed with D inversion, a NAND gate at its core. So hopefully these examples are illustrating some of the benefits of Karnaugh maps and how you can optimize significantly compared to what you see in the Boolean expression. If you took this Boolean expression and developed a digital logic circuit directly from it, very likely you would have had way too many logic gates. Counting them all off, you would have had maybe 8, 9, 10, 11, 12 AND gates, 4 inverters, and a really large OR gate with multiple inputs, which would be unwieldy at best and impossible to implement effectively at worst. But when you put it through an optimization, you see that we can reduce it over here to 3 logic gates if you use the standard development algorithm. But if you take a little bit of extra time to use all of our techniques with Boolean algebra optimization, it simplifies down to just a NAND gate. So this completes our series of Karnaugh map optimizations.